Welcome to Tetris RL by Mohammed Pablo Xiao. Tetris SLRL problem has high-dimensional state space, sparse reward structure, and takes careful planning to clear lines. As learned in class, one strategy to counteract the sparse reward is having a good initialization strategy. Specifically, we want to compare initialization of random, BC, dagger, and our own custom strategy. In order to facilitate the comparison, we need a simple learning algorithm that hopefully does not overshadow the initialization. We choose reinforce. By learning how to use initialization strategy, we can hopefully generalize this approach to effectively for other sparse reward environment. We predict the initialization strategy from best to worst will be dagger, BC, random. We hope that our custom strategy of adding a term to the reinforced loss to promote exploration will edge out all three of these strategies.
Our initial approach was to collect human expert data and train policies to predict sequences of actions to place a single piece, which is what you are seeing now. This strategy has been shown to be flawed, however, due to small errors in predicting piece placement sequences, resulting in large compounding mistakes in the Tetris environment, as demonstrated in these BC models. Our solution to this problem was to gather more data to drive validation accuracy to 100%. However, doing this would require a magnitude of more data to be collected, which is not humanly possible. We searched for an expert policy instead. Most online experts place pieces directly onto the board and leave the actions required to physically move the piece to an algorithm. Additionally, by using this technique, we can now apply common sense heuristics to rank board states such as number of lines cleared, holes present, board bumpiness, and maximum aggregate height. We decided to include all these in our heuristic along with the height data for each column to give a better description of the board. By adapting this technique, we were able to automate the collection of data, allowing for more data to be collected. Additionally, we were skipping extraneous intermediate states and were able to cover a wider range of states with less moves. Mark III wildly underfit the problem, so we increased dropout probability and increased model complexity to create a new model architecture, Mark IV. M4 requires more training, so we addressed it by filtering out the worst performing expert trajectories. We trained 3 dagger models, one trained with a random initialization, one with the BC start, and one with the BC start and BC data to start the dagger training. Each subsequent model performed better than the former, matching our intuition from class.
After developing stronger BC and dagger models, we decided to test them on reinforce, but were disappointed to see a reward of -90, the worst possible reward in our environment, along with surprisingly a training loss of 0, which is not expected for a complicated environment like Tetris. We had to perform various fixes to change this behavior. Mainly, we had to clamp the logits returned by our model, as when our model does training and gets extremely large logits, Torch actually takes those extreme logits to have all probability 1. But eventually we fixed this and got the results of random initialization being worse than BC, being worse than dagger, matching our hypothesis. Reinforced training on BC and dagger initializations had the behavior of a massive gradient in the first step, followed by a couple small gradients, which seemed to indicate that reinforce moved away from the initialization and then did its own thing. And this doesn't really fit with our goals because we want the initialization to be important. So it seemed that conservativeness to bring reinforce back to an initialization was needed instead of exploration. We implemented conservativeness through an averaging of our current model and the initial model through various points in the training epochs. We tried various weights and found that 0.2 being the new model and 0.8 being the initialization model performed the best. Overall, this graph shows our results from this entire process. We found that increasing model complexity and more data helped BC as shown in the first 4 bars. We found that random initialization was worse than BC, which was worse than BC with data for dagger training as shown in the next 3. Finally, we found that random was worse than BC was worse for dagger for reinforce as shown in the next 3 bars. These 3 results were expected, but we also found that average reinforce edges out reinforce to slight differences in variances, but not significant enough, and we should optimize further. This one was not as planned, but made the most sense to us at this point.
Some of the key takeaways we have: first, sparse learning environments are difficult to learn from, but initializing with descriptive pre-trained model can significantly boost performance. 2, abstract away as much of your problems as you can as you easily implementable algorithms. Then apply machine learning for critical decisions that can be abstracted away. 3. Research online to see what others have done to solve similar problems and build off their work to create new solutions, but do not trust the correctness of a Python library from an individual contributor, even if they have OpenAI in their name.